With this video, we begin Chapter 3, entitled Atoms, the Building Blocks of Matter. In this chapter, our goal is to develop a better understanding of the atom. Let me talk about the sections that make up this chapter. In Chapter 3.1, Foundations of Atomic Theory, we will talk about why we believe the universe is made up of atoms. That is the topic of today's video. In Chapter 3.2, we'll talk about the structure of the atom, to answer the question, what is inside an atom? And in Chapter 3.3, we will talk about counting atoms. How do we count the number of atoms in a sample of an element? You'll see it's very straightforward. So let's begin with Foundations of Atomic Theory. And I begin with the question, what is a natural law? A natural law, or a scientific law, is simply a summary statement based on multiple repeated observations that simply describes how the universe always behaves. This is how the world works. For example, gravity. When you drop an object in the Earth's gravitational field, it always falls towards the center of the Earth. Okay? Well, we're going to talk about three natural laws that describe mass relationships in chemical reactions. And they are the law of conservation of mass, the law of definite proportions, and the law of multiple proportions. And for each of these natural laws, what I'd like you to be able to do is to explain the law in your own words, and then to show how a given set of data is consistent with a given law, or predict the outcome of an experiment using the law. And let's start with the first one. The law of conservation of mass, I'm sure you're familiar with. It simply says that in ordinary chemical and physical changes, mass is neither created nor destroyed. If I carry out a chemical reaction and carefully measure the mass of everything I start with, let the reaction take place, and then collect and carefully measure the mass of everything I end up with, I will see that the masses are equal. Mass is neither created nor destroyed. Here's an example. If I burn sugar in oxygen, I form carbon dioxide and water. If I start with 100 grams of sugar, you can easily show that it takes 107 grams of oxygen to completely react with it, for a total mass of 207 grams. If you carefully collect and measure the mass of the carbon dioxide and water, you'll see you get 147 grams of carbon dioxide and 60 grams of water, which is also 207 grams. So we see that mass is conserved. Here's an example of the type of problem you can solve using the law of conservation of mass. Ammonium dicarbonate is a chemical compound, and when I heat it up, it decomposes to form ammonia, carbon dioxide, and water. If I decompose 500 grams of ammonium carbonate, I find that I get 109 grams of ammonia and 282 grams of carbon dioxide. How would you predict the amount of water that's formed? Well, here is the equation written in words. Ammonium carbonate forms ammonia plus carbon dioxide plus water. If I have 500 grams of ammonium carbonate to start with, and I know the masses of ammonia and carbon dioxide, and I want to figure out how many grams of water, I will simply use the fact that I know that the total mass of the products must be equal to the total mass of reactants. So I can simply take my 500 grams of ammonium carbonate, subtract the sum of the masses of two of the three products, and that gives me the mass of the third product. I will get 109 grams of water. How do I know that? Because the law of conservation of mass is a natural law. It always happens. The second natural law is entitled the law of definite proportions. This one is a bit more complicated. It says a chemical compound is always made up of the same elements in the same proportions by mass. So for example, if I take a given chemical compound and chemically decompose it to the elements that make it up, not only will I always get the same elements, but I will always have them in the same relative masses. For example, table salt is sodium chloride. It's always 39% sodium and 61% chlorine by mass, meaning out of 100 grams of table salt, I'll have 39 grams of sodium and 61 grams of chlorine. It is never 38% sodium and 62% chlorine. That simply never happens. A couple other examples. Water is always 11% hydrogen, 89% oxygen by mass. Methane, the main component of natural gas, is 25% hydrogen and 75% carbon by mass. And here's an example of the type of problem you can solve using the law of definite proportions. Phosphorus trichloride, a chemical compound made up of phosphorus and chlorine, is 22.5% phosphorus and 77.5% chlorine by mass. What masses of these two elements are present in a 228 gram sample? Well, I can use the fact that percent literally means out of 100. I can take these mass percentages and convert them into conversion factors. Watch this. I'll take 228 grams of my compound, which I'll just abbreviate as CPD. That's a perfectly acceptable abbreviation for compound. And if I want to know how much phosphorus is in it, I use the fact that it's 22.5% phosphorus by mass. I will convert that into a fractional conversion factor, 22.5 grams of phosphorus for every 100 grams of compound. Mass of compound cancels, and that gives me 51.3 grams of just the element phosphorus. I can do the same thing with the other element, chlorine. Again, start with the mass of compound, and now multiply by 77.5 grams of chlorine for every 100 grams of phosphorus trichloride. Again, grams of compound cancel, and that gives me 177 grams of chlorine. How do I know this works? Because if I add these together, I get 228 grams, which was the mass of the original compound. The final natural law is perhaps the most complicated. It's called the law of multiple proportions. And it says when two elements form a series of compounds, meaning the same two elements forming two or more different chemical compounds, the mass ratio of one element to the other can be reduced to a simple integer ratio. Let me give you a very straightforward example. Okay? There are two binary compounds of hydrogen and oxygen. One of them is water, and the other is hydrogen peroxide. If I take these compounds, split them apart to the elements that make them up, and measure the oxygen to hydrogen mass ratio, I obtain the values shown here. Meaning in water, I have 7.94 grams of oxygen for every 1 gram of hydrogen. Hydrogen peroxide has 15.9 grams of oxygen for every gram of hydrogen. Okay? The law of multiple proportions says that I can take these mass ratios and reduce them or simplify them to a simple integer ratio. And I do that by dividing them each by the smaller. If I divide 7.94 divided by 7.94, I get 1.00. If I divide 15.9 by 7.94, I get 2.00. A simple integer ratio. Isn't that weird? It always happens. No matter how many different series of compounds you look at, you can always do this. So the question is why? Well, we have not yet begun talking about chemical formulas, but I'm going to jump ahead and sort of let the cat out of the bag. Here is why. The chemical formula of water, as you know, is H2O. 1 atom of oxygen for every 2 atoms of hydrogen. The chemical formula of hydrogen peroxide is H2O2. 2 atoms of oxygen for every 2 atoms of hydrogen. So it makes sense that the oxygen to hydrogen mass ratio in hydrogen peroxide, the second compound, would be twice as great as that of water because it's got twice as many oxygen atoms. Isn't that cool? Now, how do we explain these natural laws? Now remember, a natural law is just a statement of how the world works. We observe the same thing over and over and over, no matter how many times we try, and we always see the same thing. Okay? That's what a natural law is. A natural law, however, does not contain an explanation or rationale. It doesn't tell you why the universe behaves the way it does. And for that, we need a theory. And in science, a theory is a broad generalization or model based on lots and lots of experiments that explains why the natural law is the way it is. Okay? A natural law is the what, the theory is the why. So, in the early 1800s, a British scientist and school teacher named John Dalton looked at lots and lots of scientific research, and he came up with a model that explains all of these natural laws. In other words, Dalton says, if you accept the 5 points of my theory, I can explain to you why mass is always conserved in chemical reactions, why the law of definite proportions works, why the law of multiple proportions works. And here is Dalton's atomic theory. Part 1, all matter is composed of atoms. None of this makes any sense unless everything is made up of these tiny particles called atoms. Atoms of a given element are identical to one another, whereas atoms of different elements are different from each other. Every carbon atom in the universe is identical to every other carbon atom, but a carbon atom is fundamentally different from a nitrogen atom. He didn't know how or why, but his theory says you need that to explain things. Number 3, atoms cannot be subdivided, created, or destroyed. Atoms are always and will always be. Part 4, atoms of different elements combine in simple integer ratios to form chemical compounds. If I want to form a chemical compound, I'm going to take 1 atom of this element and 2 atoms of that element, or 2 atoms of this element and 4 atoms of that element, and they always combine in the same whole number ratios. And part number 5 says in chemical reactions, atoms are combined, separated, or rearranged. So when we carry out a chemical reaction, all we're doing is reshuffling or recombining the atoms. So what I expect you to be able to do is to state which part or parts of Dalton's atomic theory most directly explains each of these three natural laws. For the conservation of mass, well, let me step back and say one thing. The first part of Dalton's atomic theory, all matter is made of atoms, obviously is necessary to explain any natural law in chemistry. I'm talking about which of these five most directly explain these natural laws. For conservation of mass, think about it, pause the video. Atoms can't be created or destroyed. And the other part is, in chemical reactions, atoms are rearranged. So Dalton says, I can explain to you why the mass is always the same before and after the reaction, because in a chemical reaction, we're not destroying the old atoms or creating new ones, we're simply reshuffling them. Hence, mass is conserved. That's the why. The law of definite proportions says a compound is made of atoms of different elements combined in integer ratios, and atoms of a given element are identical. So if a particular compound is always made up of the same atoms in the same integer ratios, and those atoms are always the same, then the mass ratios are always going to be the same. And for the law of multiple proportions, pretty much the same thing. Okay? Now, in our next video, we will talk about the structure of the atom, and I will see you then.